Okay, so this is our lecture 6. Today we're going to finish our discussion about the regression diagnostics. So in our previous lecture, we gave a detailed introduction to the residuals, and different residuals have different variances depending on the leverages. And then we talk about how to standardize the residuals. So by dividing each residual by its corresponding standard deviation estimate. But there's an issue with estimating sigma,
can I ask
which is a complex.
Sorry, can I ask a quick question about that?
Yeah.
How is it that usually when you fit linear models, you see that the model is pretty certain around the mean, but has a lot of uncertainty towards the edges, like where x is very far from its mean? How does that reconcile with what we saw that the residuals have?
This is exactly what we try to. So this is exactly the question I had for you guys. What does the variance of a residual mean? And I remember last time a student gave a very good answer. It's because of resampling. So that is the variance that it captures. So if you think from the resampling, means that in a fixed design, right? So in a fixed design, what we mean is that I'm just going to use the simple linear regression as an example. So in a fixed design, so let's say my x is fixed, okay? So whenever I draw a different sample, you see, if this is sample 1, sample 2, sample 3, and so on. So whenever I draw a different sample, the x's stay as it is, but the y's may vary, right? The residual, the error terms may vary. So that's what we got in the fixed design. So in other words, the center of the x bar stays the same under fixed design. What's changing is the fluctuation in the vertical axis. So then whenever you draw a line, what it means is that the line will be largely driven by the point far away from the center in x. So that will make sure that the residuals for those values, the residuals will stay as quite small in absolute values. So that's why for each xi, let's say if I call this as the x1 and x1, x1, so they're equal. So when I look at residual, here I have three realizations of this residual. I call it E1. So E1 has 3 values. Probably this is positive 0.01, positive 0.02, and positive 0.15. So you get 3 values. Across these values, you can evaluate the variance of this residual one. But if I take another one close to the center, okay, maybe I call this one as x20 or x10. Then for this x10, it has a residual E10. It's probably like this one, and it may be 0, but this one, it may be positive 3, and this one may be negative 0.3. So it has a bigger fluctuation as you repeat your sampling. That's what we talk about the variance of the residual. So it has nothing to do with the residual you observe in one particular realization. Mm-hmm. With one realization, you cannot talk about variance. Does that make sense?
Yes.
Yeah, so I think that variance just reflects, okay, if a point is farther away from the center in the design matrix, then that point has more to say about where the line goes. So you have more to say how much its own residual changes. And what was your original question, the phenomenon you raised?
Because usually when you plot linear regression, when you plot the line and you plot it with the uncertainty, then you see that the uncertainty is very narrow in the center around the mean, but it's very wide in the edges.
I think that's a different thing. That's actually what we call the prediction interval. I think that's what you meant. So it's actually the prediction interval of the yi. Okay, so if we think about it, so essentially, I believe what you are saying is this. We didn't talk about it here, and it has nothing to do with the, so it's not directly related to the regression diagnostics, but it's the prediction interval. So for that part, it's not actually in my notes. So for prediction interval, what you are talking about is the variance that is related to the variance of yi hat about this. And for this one, we know that this can be written out as xi transpose beta hat, right? That's this. And the randomness comes from the beta hat, not from the xi transpose, that's fixed. So you would have xi transpose, the covariance matrix of beta hat, xi. Okay, then here, you will get this part out. That just becomes sigma squared, that's a constant. But in the middle, you have xi transpose, x transpose x inverse xi. Okay, so that will be the variance part. So you can imagine, if this xi is farther away from its mean, then this thing, which becomes a scalar, will actually be larger, right? It's essentially just a distance. If you think, maybe an easy way to think of this is that if I standardize my columns in the design matrix, if I make my column of matrix center at 0, then or scaling it to have column standard deviation equal to 1, then this x transpose x is just a correlation matrix. And this one, and I'm just taking the inverse of the correlation matrix, and this can be considered as a squared norm of this vector xi. So for every vector, it's corresponding to a point in the p-dimensional space. This is in the p-dimensional space, but I'm centering the whole cloud of points, moving its center to the origin. And then you can see that this is basically the scaled norm of this point. So the farther away from the center, the larger this value will be. So that's why this variance will be bigger. That's the thing you're talking about. But it's not about the variance of the residual.
Okay, thank you.
Yeah. Thank you for the question. Yeah, there are also, actually, I think it's a very nice question that is, I think in linear regression, we all learned it maybe in the undergraduate class, and many people think it's the easiest model. But since it's easiest model, we can say a lot of things about it. So that makes it interpretation actually quite tricky. Yeah. Okay, so yeah, coming back to the thing I want to talk about today. So yeah, I was trying to summarize over there yesterday, last lecture, which is about the standardization of the residual. And related to the estimation of sigma, we give you the jackknife residual, which means that we exclude a potential outlier from the estimation of sigma. And then we give two equivalent interpretations for the jackknife residual. Okay, you can check the notes in the video for that. And then we talk about how do we also identify some important data points to focus on based on the design matrix only, that is the leverage, right, which reflects a potential influence. And finally, we talk about Cox distance, which is the actual influence a point has on the estimation of the beta, right? So the larger the beta hat changes with or without that point, we will say the larger the Cox distance. That's in our last lecture. So today we're going to give you two visual checks about how linear regression fit. Okay, so these are some graphics that are very useful. So visual check. The first one is what we call the residual plots, which is also what R can return to you if you just plot a linear model object. So in residual plot, what are we plotting here? So it's actually very simple. The y-axis plots the residual, EI, for all the data points, and the x-axis plots the yi hat, the fitted response. So you may wonder, why are we doing this instead of plotting EI against each predictor? In a simple linear model, you could do that because the yi is just a linear function, yi hat is just a linear function of xi. But if you're doing a multiple linear model, you will have p minus 1 predictors. Then you have to do this plot for each predictor. So that there are a lot of plots, right? Not feasible. So that's why we're plotting this against this yi hat. Again, as we know, it's basically a transformation, linear function of the estimated beta hat. And furthermore, you can see that this is actually just equal to xi transpose times that OLS formula, right? So it's still a function of y, a linear function of y, and y1 to ym. They are all incorporated into this yi hat. So if you look at this formula again, you can see that we have used a very important principle in statistics. That is, we borrow information across data points, because this one involves n data points, and we are using them together to estimate or to predict the value of one data point. So this is what we call borrow information. And please keep this in mind. This is the essence of any type of regression. It's kind of a borrow information to regress to the mean. Okay, so looking at the residual plot, what we really want is that there's no specific pattern of how the residual will look like given the fitted yi hat value. So ideally, because we know the residual is expected to have mean 0, right? All the EI is expected to have mean 0. And also, given the Gaussian assumption we had for the linear model, the EIs should follow normal distribution. So each EI should follow a normal distribution with 0 mean. And its variance, we know that is sigma squared 1 minus HII. This is depending on the leverage of the design matrix. But again, like I said, this is only one realization. We do not have many observations of the same EI, one observation per EI. So we cannot look at one EI to make a decision. Instead, we look at all the EIs together across data points. So it's possible that you will see the variance is not the same, which is actually possible because given that each EI comes from its original Gaussian, and we don't know what this, so we cannot know the sigma square exactly, right? And also each one only has one realization. So we cannot say, given this data point, we cannot talk about this variance. It's not possible. We cannot calculate variance based on one data point. But one thing we can look at is whether these points are all centered around 0 because they share the same mean 0. And if you believe that they sample from this distribution 1 by 1, from their own distribution 1 by 1, we will still expect that they would have a center around 0. So this is the thing we want to check for residual plot. If we do not see it, right? If we see there's a trend that is like this is considered good. But if we see a trend that's clearly not centered at 0, for example, something like this, then because the 0 line's here, then you will expect that something was wrong about my linear model fitting. So possibly that the model is not really fitting the data well. You need to do some adjustment. So this is the most important thing to look at, the pattern, whether it has a flat, it's centered around the flat line across 0. Okay, that's the first thing. And the second thing is that, of course, here, if you want to check whether they have a constant variance, you could use the standardized residual. That's the purpose of introducing that in our last lecture. So you can also use the standardized residual or the jackknife residual instead of the original residual for this check. And then you can expect that there should be a more constant variance. Okay, that's for the center 0 check. if the expectation of EI is 0. And the second check is to check the normality assumption. And we will use QQ plot to check the normality of residuals. So here I'll just use SI as an example. So you want to know that given we have done the standardization, then the SI, assuming there's no outliers, will be approximately standard normal, right? That's what we should expect. But is that the case? We can pull the SIs together as 1, 2, Sn, and check whether they overall follow standard normal distribution. Then how do we do that? There is some understanding about the QQ plot. Everyone uses it a lot, right, in practices. But here I want to emphasize what the QQ plot is actually about. So in the QQ plot, as the name stands, the two axes are quantiles. So one axis, usually the horizontal axis, is the theoretical quantile. And the y-axis or vertical axis is the empirical quantile. So what does that stand for? Any thoughts? Or how many dots are we going to have in the QQ plot?
N.
N, yes, it's equal to our data points in the sample size. So we have N points, right? And then what are the empirical quantiles? That's based on the empirical distribution. So basically, each data point, maybe I'll use a blue paper to show that. So let's say that I have sorted my S1 to Sm. We know in statistics, we use the notation for order statistics. So that stands for the sorted standardized residuals. Okay, then we know based on the empirical distribution, the probability associated with each value would be, this is the left tail probability, okay? That the empirical distribution has below or equal to each value. This will be 1 over n, 2 over n, up to n over n. That's the empirical distribution. Then correspondingly, we would have this one is equal to the 1 over n quantile. This is the 2 over n empirical quantile, and this is n over n empirical quantile. Okay, these are the empirical quantiles. Then correspondingly, we should find theoretical quantiles with the matched probabilities. So for theoretical quantiles, here we are just using standard normal as the theoretical distribution. Then the quantiles would be, I find 1 over n here and pick the value, and another 1 over n here, pick the value, and so on. So these will give me the corresponding theoretical quantiles. Then what I will do is that I will plot the S1 to Sn on the y-axis and the corresponding theoretical quantile, these values from the x-axis. That's the QQ plot. And I'm trying to make it simple to start with so we understand the concept. But one thing we need to account for is that if you stick with that Sn is the n over n or 100% empirical quantile, then you have an issue to find a theoretical quantile here. Because if with probability 100% or 1, the theoretical quantile for standard normal will be positive infinity. And you're not going to plot it here, right? There's no way to plot a positive infinity. So in practice, in the QQ plot, we are not treating this one as 1 over n. We're not treating this one as n over n. Instead, we will do some adjustment, small adjustment in the numerator and the denominator. to make this not 100%, and also to make the two sides symmetric. For example, if this is like, let me make it up. So maybe if this is 1/2n, and then, sorry, I would say maybe this is 0.5 over n, and this is probably n minus 0.5 over n, something like that. So you try to make it symmetric so that you can avoid that positive infinity or negative infinity issue in the theoretical quantile. Okay, so if you realize that, then we can think of what does a pattern in the QQ plot indicate to us. So if you think about a bad QQ plot, okay, so if we have this bad QQ plot, again, this is theoretical quantile, this is empirical quantile, then what we see, the ideal case is that the line would be diagonal. That's the ideal case. But what if you observe that the QQ plot looks like this? Then how do we interpret this? What this implies is that when the quantile is small, which tells us, okay, we are on the very left end of the distribution. When it's small, the empirical quantile is larger than the theoretical quantile. So being larger, it means that, okay, let me give you two distributions. So one is this, the other is this. Okay, so let's say on the left tail, clearly, maybe I'll use different color. So one is red, one is blue. So you can see that the red one has smaller density on the left end. So therefore, to receive the same left tail probability, I need to move more to the right. So that probably over here, the left tail probability under the red curve would be equal to the probability under the blue density. So then in this case, the red quantile would be larger than the blue quantile. So that's the case we see here, right? So you have a larger empirical quantile than the theoretical quantile, which means what? Which means that compared to your empirical distribution, which is red, the theoretical blue distribution is too heavy-tailed. So that's one indication that probably you are not assuming a correct distribution. The theory is too heavy-tailed compared to the empirical distribution. So I'm just trying to use this as an example so that you can kind of relate the QQ plot pattern to the understanding of the model fitting. So you don't need to memorize, okay, which pattern corresponds to which if you understand the essence of QQ plot. Just try to make figure yourself and then think about the relation between quantile and the left tail probability. Okay, so I hope that's clear. And also there are some tests to check whether normality is a good distribution. For example, we know a general test to check whether data states a certain distribution is to use the Kolmogorov-Smirnov test, short as KS test. But one thing we need to be very certain is that the KS test is a very sensitive test, which means that as long as the null hypothesis does not hold for sure, that means if your data comes from some small deviation from the null distribution you assume in theory, then as your sample size gets large, you will reject the null for sure. That's just the essence of statistical tests. We know that for any test, if your data do not exactly come from the null distribution, then when your sample size goes to infinity, your power will go to 1. That's just the nature of a statistical test. So what does that mean? It means that if you have large enough sample, you are going to reject the null for sure. But sometimes, you know, for our sanity check, we can allow for small deviations from the theoretical distribution. So that's why I'm not talking about the KS test here, because I feel like that's usually too stringent. Even though your eye may inspect, hey, the QQ plot looks reasonable, still the KS test may give you a very small p-value. So that's just something to keep in mind. So I would say in applied statistics, the very important technique is to make plots, to make graphs, so that you can use your eye to make some subjective judgment in addition to the p-values that the test gives you. Okay. Of course, in our notes, we said there's a Shapiro-Wilk test specific designed for checking normality. So that is similar in terms of the using p-value to help you guide your decision. Okay, so that's just the two graphical checks. And then one last thing I want to introduce is data transformation. So what if I check my model and if the fit does not seem to be reasonable, what can I do? So there are some ways to transform your data, which is usually easy to implement. So you can still use linear model, but not on your original data, instead on your transform data. So data transformations. Of course, since our data is composed of a response vector Y and N by P design matrix X, right? That's our input data. So of course, we could consider transforming Y or transforming X. So first, let's think about transforming Y. So the technique we're going to introduce is a very classic technique called Box-Cox transformation. So you must have heard of the two names Box and Cox in other occasions. So Box is the one who gave the famous saying that all models are wrong, but some are useful. That's the George Box. And David Cox is the one who is very famous for Cox regression in survival analysis. Okay, so this is a work from 1964. And so what they did is that they give us a systematic way of choosing a power transformation on our response Y. So here I'm just going to talk about it for one particular response yi. So it says that by introducing another parameter lambda, you could consider for each lambda, you can consider a transformation. So for lambda being positive, okay? So it gives us special case for lambda being 0. So in this case, it says that you would just transform yi by taking the log. But of course, here you see, if you want to take the log, you need to first move your yi to be positive. Otherwise, the log transformation will be invalid. So this requires that you make yi positive by shifting y1 to yn, right? You can always do the shift yourself so that the minimum of the yi's is still positive. Okay, and for other lambda positive, you could consider, oh, I should say, probably, I think like that. No, I think I don't need this, sorry. For other lambda not equal to 0, you do power transformation. That is, you do y to the lambda minus 1 divided by lambda. You can see why we want to do this. The reason, I think, for deriving this form is that if you do derivative of yi, okay, if you take the derivative of yi, then you would have, this one becomes lambda times yi to the power lambda minus 1. And that lambda will be canceled with the denominator. So the derivative will be yi to the power lambda minus 1. And the same derivative will be for log yi, right? If you take derivative, become 1 over yi, which is yi to the power negative 1. So in other words, what you do is that if you do dy lambda, the result you get is always yi to the power lambda minus 1. I think that's why they derive this form for the transformation. So you can see you have many power transformations that can be applied to the response. So then given a transform y, our model, linear model, is going to be about the yi lambda instead of the original lambda, instead of original yi. So therefore, as I said, we will always write down the random structure and the systematic structure of our linear model. So we'll do the same thing for the generalized linear model and the multi-level linear model we'll talk in the end. So this is the habit I want everyone to accumulate so that you know whenever I specify a model, I'm very clear what is random, what is systematic fixed. So here the random structure becomes yi lambda itself follows a normal distribution and is independent for i's with its own mean mu I and the same variance sigma square. And the systematic structure for each I is still linear, xi transpose beta. So this stays the same, but the random structure is changed by changing the random variable from yi to yi lambda. So therefore, given this model, you can still write down the likelihood, right? The likelihood now is a function of 3 parameters, beta vector, the variance sigma square. Now the new parameter lambda also needs to be included. So let's just quickly say that we would be having this likelihood. Okay, I'll write it as beta sigma square lambda. And we know the likelihood is defined as the joint probability density of our data given the parameters. So therefore, it's the product I go from 1 to n. This is thanks to the independence of the density function of my yi to my yi transform lambda given these parameters beta sigma square lambda. Okay, so that's it. So then this is the function, this is the density function based on yi lambda. But one thing we need to be clear is that if we are going to, sorry, I should say this. So this is the density function we write based on, I should say this, sorry, do this. So this is the density function, joint density of our data, okay, y1 to yn. But now to write down this density, we need to use the random structure. And the random structure is specifying the distribution of yi lambda instead of yi. So it's about a function of yi, not a yi itself. So to address that, we need to consider what we call the change of variable for probability density. So what we mean here is that, so in the change of variable for probability density is this simple formula. So let's say that we want to have the density of y. Okay, we call it probability density f. And we know that y itself has a 1-to-1 map with another random variable x, whose density function is g. Okay, then how do I link those two? So the way to do that is to add this absolute value of derivative. So I'm talking about one-dimensional random variables. X is one-dimensional, y is one-dimensional. The two densities are one-dimensional. Otherwise, we need to talk about this as a Jacobian matrix and its determinant. Okay, so then we take the derivative of x against y. So then you can express the density of y in terms of the density of another variable x. So this may seem a little abstract, but maybe it's easier for you to see that in a concrete case. So for example, if x equals y squared, okay, they have a 1-to-1 map, and then my f, so I should say x equals y, I shouldn't say this is a 1-to-1 map. This is just a onto map, right? So this is just a function, I should say. It's not 1-to-1 because we cannot go from y to x. So here, but the function is okay. So x, it must be a function of y. I should say that. Then fy is equal to gx, x is y squared. Then I plug in y squared, and dx dy is 2y, the absolute value. Okay, so that will be the density of y based on the density of x and based on this transformation. That's the change of variable. So essentially, what we need here is we want to derive the density of yi given what we know of the density of yi lambda. So yi lambda becomes our the density of yi lambda becomes our g, and the density of yi becomes the f we need. Okay, so probably to help you understand this better, I'll call this f so that you are not confused about it. So then by applying this change of variable, the density of yi, of course, given beta sigma squared lambda, I'm ignoring the parameters, it will be equal to the density of this yi to the power lambda, for which we know the density is from normal distribution, times the absolute value of the derivative of yi lambda against yi. This is why we care about the derivative here. You see, the motivation is now clear. We want the derivative to have a nice formula that motivated us to have the form in the Box-Cox transformation. The reason is that we need this derivative in the change of variable formula. And then we're done. Okay, so you see that this is the g yi lambda, which we can write down as normal density. If you want me to write it down, it's actually very straightforward. Just 1 over 2 pi sigma exponential negative 2 sigma squared here, yi lambda minus mu I. Or mu I can be replaced by x and transpose beta. Then you will have beta here. Okay, this will be the normal density. And additional term, which is the derivative, is just this yi to the power lambda minus 1. Okay, and of course here it must be positive. So I'm also assuming that the yi is made positive, just as what we did for the log here. So please make sure that when you apply the Box-Cox transformation, you do the shifting first. Okay, so that's the density. And you can make the density into your likelihood to do the product, and you are fine. So then let me simplify this whole thing. Then you can try the algebra yourself, but after the simplification, the log likelihood just becomes, I'll use the lowercase l for beta sigma squared lambda. The log likelihood just becomes negative n over 2 log 2 pi sigma squared minus 1/2 I from 1 to n sigma squared yi to lambda minus xi transpose beta squared. Okay, and the third term is plus lambda minus 1 times summation log yi. This is from the last term. After you take the log, the lambda minus 1 comes down. So this is our log likelihood. And we're going to maximize it to find the parameter beta, of course, the key parameter, sigma squared, again, will be need, and also lambda. So you could jointly maximize this log likelihood so you can select the transformation on your y, which is determined by lambda. Okay, and then how do we do the maximization? This is some concept we can use for solving this problem. It's a very interesting concept. Maybe some of you will have seen it or will see it, but it's actually not that difficult as its name stands. So this is something we call profile likelihood. Okay, by profile likelihood, it means that when we maximize the likelihood, we fix some parameters first and maximize the likelihood by searching for another set of parameters. So to be specific here, we don't consider lambda first. We just take it as a random, as any lambda, I should say, any lambda value. And given that lambda value, then this term no longer matters, right? To maximize the likelihood based on beta and sigma square, I'm left with the first two terms. And that's in the standard maximum likelihood setting for linear model. So we know the formula for the beta as the least squares and the sigma square based on the residuals. So those two formulas are still there, right? So given, what I mean is that given lambda, I could derive beta hat as a function of lambda from the MLE, from maximizing this profile likelihood. So I would have X transpose X inverse X transpose Y, but this Y is Y lambda, right? The transform Y. And then the sigma square hat given lambda. This is still what we are familiar with. This would be the, I would say, maybe I'll just use the vector form. So Y lambda minus Y hat lambda, right? So this is the fitted vector for response transpose Y lambda minus Y hat lambda. So when I do this, I'm getting the sum of residual squares divided by n minus p. So I will have the MLE for beta for sigma squared given lambda. Then I can obtain what I call the profile likelihood for lambda only. So the profile likelihood if you think from the name, is what the name, that was what the word profile means. It's from just one angle. And then usually we give it the notation LP. P stands for profile. Now we're only left with one parameter lambda. Then this profile likelihood is defined as the likelihood with beta replaced by beta hat lambda, sigma square replaced by sigma square hat lambda, and lambda. So then you see the only remaining parameter is lambda. Then you will find lambda by maximizing this profile likelihood, and you are done. Okay, so finally, lambda hat is the argmax of the profile likelihood of lambda. That's the solution. And then the question I have for you is that if we use this profile likelihood approach, and then you see with this, sorry, I'm not done yet, then beta hat will be set as beta hat, lambda hat, and sigma square hat will be set as sigma square hat, lambda hat. Okay, once we fix the lambda hat, we plug it back into the two formula. Oh my God. So then my question for you is, does this profile likelihood approach actually give me the MLE for maximizing the log likelihood, the original log likelihood? That's a question for you to think about.
I want to say no, but I'm not sure.
So if you think about it, so I think it's tempting to say no. I would say it's tempting to say no because it seems that you are not fully using the function information, right? When you try to find the maximizer for beta and sigma squared given a particular lambda. But actually, if you think from it, so first of all, let me give you one simple answer. That is, if the likelihood function is convex, then you don't have an issue there, right? or concave. If it's concave, then you don't have an issue. You shouldn't have an issue at all. But if it's not concave, then that will introduce some tricky things like a saddle point, those kind of things. But even for that special case, if you think of it, still, we should be fine. The reason is that basically when we do the profile likelihood, in this case, we just, even though we given each lambda, we try to find the maximizer of beta hat and sigma hat square. Then when we plug them back into likelihood, we are still evaluating this for every given lambda. So then you can see that we didn't lose much because we still keep all the possible lambda into our consideration. So actually the answer is yes, the profile likelihood approach is valid for finding the MLE. But later, as we talk about the multi-level model, we will tell you that we need to be cautious when we talk about the variance of the MLE. Basically, the short message is that if you are using the full likelihood, you could directly use Fisher information to derive the asymptotic variance for MLE. That's just a valid result. But if you're using the profile likelihood, which is not a real likelihood, this is not a real likelihood, you cannot just use its Fisher information to derive the variance for lambda hat. So you cannot use that property of likelihood. So we'll talk about that later. So we'll talk about how to use the likelihood to talk about to define the score function, Fisher information, and variance of MLE. Okay, so that's the Box-Cox transformation. In practice, we didn't actually try to consider all possible lambdas to maximize the profile likelihood. It's not usually that necessary because we also want this lambda to be some simple number so people can easily interpret whether it's a quadratic transformation, whether it's a square root transformation. So usually we consider lambda to be those 5 values, -1, 0, 1/2, 1, and 2. So basic 1 means we don't do a transformation, 2 is the square, 1/2 is the square root, this is the inverse. That's the usual transformations we consider. Then it becomes simple. You just use those 5 numbers to evaluate which one maximizes the profile likelihood, and you're done. Or you could actually go here, right? You consider each of the 5 values, consider the corresponding beta hat, sigma square hat, plug them back in, and then evaluate the likelihood, and you're done. Okay, so that's the Box-Cox transformation. And what if we transform X, transform our design matrix? This is what's very useful. This is a common practice for linear model. Usually, we will see that maybe the original predictors as they're provided are not very predictive. We may want to do some nonlinear transformation on the design matrix. And this is actually fundamentally, this is the essence of our neural network, right? In neural network, after each layer, you apply some nonlinear transformation to your features, to your transform features. Okay, so here, when we do those nonlinear transformation, again, we usually consider these options, okay? But one thing to keep in mind is that when you do the transformation, you need to consider collinearity between your predictors. Because usually what you do is that instead of just using your original xj, okay? So let me call this xj the jth column in the design matrix. Okay, that's a vector, n-dimensional vector xj. So one thing to keep in mind is that if you do the transformation for each element in xj, I call that xij to be consistent with our notation. If you do xij squared, okay? So if all the xij are positive, then you do quadratic transformation. We know the line looks like this. So you could see that this xij squared would be highly collinear with xi. So basically, this xj squared is collinear with xj. So in other words, the two vectors Pearson correlation is very positive, right? It's very positive. That's what we mean by collinear. And this will cause some instability in the parameter estimate, right? We know that this is something we need to consider again. This variance matrix of the beta hat vector depends on this inverse. So what we would have is that if we have two entries, so let's say one entry corresponds to beta hat for xj, its coefficient. Another is beta hat for xj squared, this coefficient. So if those two predictors are highly collinear with a large correlation, reflected in here, like I said, if the matrix can be considered standardized, then this is the correlation matrix, and we're taking the inverse of the correlation matrix. So large entries in the correlation matrix will actually inflate the diagonal entry in the inverse matrix. So basically, you'll make this variance larger, this variance larger. So in other words, if you care about the parameter themselves and talk about the inference problem, whether beta xj is 0 or not, you're inflating the variance in your estimate. So that's something we want to largely reduce by creating new features. We want to reduce the collinearity. So then the practical consideration is that when you do the square, you first center your column to be 0 centered. So in other words, your xij will be evenly scattered around the 0. And then when you do the quadratic transformation, you keep the sign. So this will be for the positive part, this will be for the negative part. So in other words, your transformed xij squared will carry the same sign as the xij. And you do the transformation after you centered the n entries in the j column. Okay, so this is a practical way of this. Oh my God, let me see this. So no, this is still calling that. I mean this, right? If you do this, if I don't keep the sign, then I reduce the collinearity like that. Yeah, so because for the negative part, their square will be positive. So this new xij square, was not collinear with xij. That's a practical consideration. And the reason I made the mistake just now is because I want to talk about the quadratic, about the square root. So for the square root, yes, in that case, after the centering, okay, some are positive, some are negative. I need to consider the sign before I take the square root. So for the positive part, I just take the square root. For the negative part, I need to take the sign multiplied by the sign, so it becomes negative xij before I take the square root. So doing so, I can also avoid the collinearity. If you imagine that if I don't do the centering, and if all my xij are positive, then the square root values will still be collinear with xij because they have a positive correlation. Okay, so these are just the considerations we apply to xij. And also you can consider a similar thing can be applied to log, right? Because if your xij are positive, take a log, it will have a strong collinearity. But if you do the centering and do the log similar to the square root, then you can avoid the collinearity. Okay, so another name given for this is what people call feature engineering, which is very common in the current data science, right? You need to worry about the data, not just the model. Okay, so that's all for linear model. Finally, we concluded all the simple but quite tricky details in linear model, linear regression. Now, so our next topic, we're going to move on to generalized linear models, and we are going to start with logistic regression. So before we do that, do we have any questions so far?
Is there a like a simple rule on when to use log transformation on X?
No, I would say it's just a trial. We just try different transformations and see which ones are more reasonable. So I would say for this part, what people call EDA, exploratory data analysis, a term coined by John Tukey, is very important. So you want to play with your data for every feature, every column in your X. You try the transformation, and then you just plot each transformation against the response to see if there's some linearity or correlation between the response and the transform feature. So that's usually the most intuitive way of engineering features. Yeah, and I would say that neural network has simplified this a lot for us. You can consider neural network or deep learning as a way for doing automatic feature engineering from those unstructured data like images, so that it saves us the human trouble of doing this by ourselves. But I also heard a saying from a professor in computer science at a seminar talk, is that for every black box model, if you try really hard, you can always find a simple model with good performance. So the trick is that you basically apply the feature engineering first, and then on your engineer features, a simple model will give good prediction. Yeah. So it's just where you place the labor at. And I know that when I work with some scientists, they usually prefer this manual feature engineering, because if they really want to dig into the data to find some scientific truth, it's very important that you understand what transformations you did without relying on black box algorithm to do the job for you. Yeah. But for industry applications, I think people are usually more tolerant for black box algorithms, because usually the goal is to do good prediction for application purpose, and it's not to really understand the mechanism. Okay, so yeah, so if there are no more questions, let's move on. Now we are going to start our second most important topic, GLM, Generalized Linear Models. So let me give you an overview of what is GLM. So still, this can be understood in terms of the model structure. So what's changed is the random structure and also the systematic structure. So this is just the overview, and we're going to delay the formal introduction to the GLM theory later. But for the overview, you can think of it that in the GLM, the random structure, how yi is distributed, we still keep the independence assumption in relation to mu I. Okay, so it's distributed for some function involving mu I. Or maybe I should put it as f mu I. So mu I is the mean parameter of some distribution, f, and yi follows that distribution. So when we generalize, this f mu I is no longer the normal mu I sigma squared. That's the generalization. We're not assuming normal distribution anymore. And for the systematic structure, we also have some generalization. We're not assuming mu I is directly a linear function of predictors. Instead, we're assuming that subject to some transformation g, function g on mu I, this g mu I is a linear function of the predictor. So the g is no longer an identity function. So these two generalizations give us GLM. So we're going to use the logistic regression to open the topic and see how it generalizes the random structure and the systematic structure. Okay, so logistic regression is, I would say it's a very interesting method to learn about, because it has two flavors. One is that it's a very good model for inference, just like our linear model. We can talk about the parameters beta j's to say, okay, whether this predictor has an effect on my response or not. We can talk about those inference problems. We can also use it for prediction purpose as a classification task And sometimes logistic regression works very well for binary classification. And it also has a very natural version for multi-class classification. So that's why logistic regression serves the purpose of both prediction and inference. You can say that the linear model also serves two purposes, but usually people do not think linear model can do a very good job for predicting unless you try really hard with feature engineering, like we said. But logistic regression, on the other hand, people still think in many cases it does a very good job for prediction, especially if you use high-dimensional logistic regression plus some penalty like lasso, ridge, or elastic net. So using those penalty, you can overly parameterize your model by including more predictors than your response, than your observation, than your sample size n. Then use the penalty to help you screen down those important features. And those can usually give you a very good prediction performance. Okay, so first of all, let's talk about logistic regression for binary data. And then we will talk about its extension for count data, not binary data. So for binary data, each response is binary, okay? Takes two values, 0 or 1. And many data are like that. For example, in the current scenario, if we talk about vaccine, right? Effectiveness of vaccine on people, then each person after he or she received the vaccine may still have infection, which we can mark as 1, or no infection, which we can mark as 0. So the response is binary. And if you want to see which predictors are associated with the response, then that's a logistic regression problem. In another scenario, we can think of the response as votes. So whether the person voted yes or no in some ballot. And then we can look at whether that person's characteristic like gender, age, education level has any association or effect on the response. So these are all the settings for logistic regression. So clearly you see, for logistic regression, those binary response, we cannot assume linear model anymore because clearly these binary I will not follow a normal distribution, right? That's another even reasonable assumption. Then what distribution do we assume for binary? There's only one distribution, Bernoulli. Bernoulli is the only distribution that can describe randomness in binary data. So clearly, the random structure is set yi independently follow Bernoulli with mean. So here, let's just give it a name, pi I. So basically, pi I is what I call mu I here. It's just for convention, we call pi I. And of course, this pi I is between 0 and 1. Okay, now think about the systematic structure. Think about the systematic structure. And for each pi I, we're going to link it with the linear part, xi transpose beta. And the predictors can take any values, right? Any real numbers can be our predictor values. So, and we don't have any constraint on beta as well. So you could see that this xi transpose beta part, its possible value actually is from negative infinity to positive infinity, or the real line. And clearly, pi I is constrained to 0 to 1. It's not covering the whole real line. So it's not reasonable to assume pi I equals xi transpose beta. But then how can we match the two? So the possibility is that we can consider how to transform pi I using the g function so that g pi I is in the real line, can take real values, not just 0 to 1 values. That's the key point. And one function we know that works very well is what we call the logistic function. The logistic function is essentially the logic is the, okay, so probably let's start from here. So 2 steps together. So this one is not good, right? But what if we consider pi I over 1 minus pi I? This one is actually better. So we know that when pi I is 0, this will actually give me what? 0 to infinity. So I can get positive infinity with this because I'm going to divide 0. Okay, so I'm actually going to go from here to here. So I can have very, very large positive numbers using this ratio. But not yet. I'm not covering the negative part of my real line. What do I do? For that, I can take the log, right? Taking the log for value from 0 to 1, after log, it will become negative infinity to 0. So if I take log once more, I would have the range from negative infinity to positive infinity, which matches the range of xi transpose beta. So this is exactly what we have defined as the logic function. So it's defined as logit pi I. So it's basically the log transformed pi I over 1 minus pi. So the systematic structure is logit pi I equals xi transpose beta. And that's it. Okay, this is the logistic regression model. And for the logic function itself, we can actually give you a visualization to help you understand. So let's say that this is 0 to 1, okay? And this is 0 to 1 for pi I. The y-axis is logit pi I. It goes from positive infinity to negative infinity. So the logic function will look like this. So when pi I is equal to 0.5, the logic function is 0. Now when pi I is approaching 1, the logic function is approaching positive infinity. And it's symmetric for the left part. When the pi I is reducing from 0.5 down to 0, the logic function is approaching negative infinity. So you see that this transformation exactly satisfies our desire. We transform value from 0 to 1 to negative infinity to positive infinity. So this logic pi can be reasonably assumed as a linear function of x and beta. Okay, so in the context of GLM, usually people give this transformed mean parameter of the ith observation, ith response. Usually people give it a notation called eta I, just for notation convenience. So this eta I is directly assumed as linear function. So in other words, what we wrote is that here, we basically wrote it as G mu I equals xi beta transpose beta equals eta I. So this eta I is defined to be representing xi transpose beta. And it has a name. So it's called linear predictor. Okay, to summarize, what we meant is that in the random structure, we assume the random response yi follows some distribution with mean parameter mu I. And the mean parameter mu I subject to some transformation is called the linear predictor. The linear predictor has a notation eta I and is written as xi transpose beta. Okay, so it's just a notation convenience, nothing special. And also as a jargon, there is a name for this G function. This G function is called the link function. And what the link function does is to transform the mu I parameter to the linear predictor. So it links the parameter to the linear predictor. Okay, that's what it's called, linear link function. And the link function, as we know in the linear model case, is just identity function, no transformation.
Professor?
Yeah.
Does the link function have to be invertible, or can it?
Yes, it has to be invertible. Yeah,
okay.
It is a very good point. Because we need to apply the inverse of the link function then in our MLE derivation. Yes, I should put it here. So based on this constraint, and we know the linear predictor takes real values, that gives us some rationale or criteria, criteria for selecting a reasonable link function. And we'll see that logistic regression is just one. This is just one of the possible link functions for binary data. And we also have, in the history, we also have probit regression, which applies the inverse of the standard normal CDF as the link function, which can also serve the purpose. So we are going to do some discussion on that after we finish talking about logistic regression. Okay, so this is the logistic regression for binary data. Then how do we consider the effect beta J? This is very important regarding the inference and interpretation. So we know that, okay, so logit pi I, or let me write it out, log pi I over 1 minus pi I is equal to xi transpose beta, right? I can also write it out as this j from 1 to p, xij times beta j in the scalar form. Oh, sorry, I didn't show it. Yeah, I can also write it out in this. So in other words, I'm interested in this beta j. So beta j is the effect, people call that effect size of predictor j minus 1, right? Because the first one is the intercept, we exclude that. So then how do I evaluate or understand this effect on my response? So if you think about it, you actually have this relationship. That is pi I, okay, can be written as exponential xij beta j divided by 1 plus exponential xij beta j. So this is the relationship between these two. So basically what this beta j has as an effect on pi I is through this function, right? When you increase beta j by 1 unit, you are increasing this power you're increasing the exponent in exponential function by 1 unit, and then it's affecting pi I through this complicated exponential divided by 1 plus exponential on pi I. And that's affecting the probability that your yi is taking value 1. So in other words, here, the effect size of predictor j minus 1 is through this indirect way, it's affecting the probability in this function, using this function, and then the probability will determine how likely yi takes value 1 instead of value 0. But please be aware that we have randomness encoded in Bernoulli. That is, as long as pi I is not equal to 1, there's always a chance for yi to take value 0. So that's the randomness. So we'll conclude here for today. But here, my left question left for you as a take-home question is, please think about what is the error term here? Do we still need an error term in our logistic regression? In the Gaussian case, in the linear model case, we have error term to capture the variation along the above or below the line, right? The variation of the random error term. But here, what is the random error term? Do we need that one or we don't? Okay, so that's a question for you to think about before we return on next Tuesday. Okay, see you. If you want to stay in the chat, in the room to chat with your peers or with me, you can stay.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Hey, can I ask a question?
Yeah.
one second. Okay, about the final project.
Yeah.
So currently it's supposed to be a review, some review of existing method.
Yeah.
I was wondering, since I like in our lab, I work with linear models. I was wondering if it's possible to use some existing project and maybe just create like some sort of test case. What I mean is, for example, I'm working on this problem. First, I tried this linear model. And then analyzed it had this and this fit. This is the inference. Then I tried to apply some transformation. This is the result. Then I'm trying to make like an intercept, a multi-level model with a varied intercept. These are the results.
And so this project is not supposed to be project-based. It's not about a data analysis project. It's supposed to be a literature review. So I want to use this opportunity to encourage students to read papers and summarize the papers. That's the purpose.
Okay.
Yeah. Yeah.
Okay.
Okay.
Thank you.
Okay. Bye.
Bye-bye.
Bye-bye.